Usually, when we talk about getting a medical diagnosis, there is this fundamental expectation of precision, right?
Oh, absolutely. We want a clear-cut answer.
Yeah, exactly. You think of it kind of like engineering. Like you
Right.
break your arm, they take an x-ray, and the doctor points to that jagged white line on the screen and says, there it is.
Right. It's either broken or it's not broken. It's binary.
Exactly. Binary. It's a clean, observable fact. You are literally looking at the mechanics of the reality right in front of you.
And we find a lot of comfort in that, you know?
Yeah.
Human intuition just craves the ability to categorize the physical world by simply looking at its underlying structure.
But then, and this is where it gets interesting, you step into the world of, say, neurodevelopment or psychological trauma, and suddenly that x-ray machine is totally useless.
Right. The whole paradigm shifts.
Yeah, you're suddenly looking at a diagnostic landscape that is incredibly murky.
Yeah.
It's subjective. It relies entirely on testing symptoms rather than observing actual structural causes.
Which is the absolute definition of diagnostic muddy waters, really.
Exactly. You basically just throw tests at a patient and wait to see what behavior bounces back. And for the last couple of thousand years, the brightest minds in human history have looked at the fundamental building blocks of mathematics prime numbers. And they have basically been acting like psychologists instead of radiologists.
That's a perfect analogy, actually. We haven't had an X-ray machine for the integers. We didn't have one.
Right. So we've been operating in the dark. Welcome to our deep dive on the prime gap structure. I'm so glad you were joining us today, because we are going into some truly mind-bending territory.
It really is. Mathematicians have basically been forced to treat the prime numbers as this domain of pure, unadulterated chaos.
Just totally random.
Exactly. The standard operating procedure, going all the way back to Eratosthenes and stretching right up to modern computational number theory, has just been to treat primes as these wild, unpredictable entities.
Like they're just scattered completely randomly across the number line.
Yeah, exactly. We didn't have a structural blueprint. All we had was symptomatic testing.
And that assumption of chaos, I mean, it has been formalized. It is literally baked into the textbooks.
Oh, absolutely. It's the foundation of how we teach number theory.
Right. We are taught that as numbers get larger, primes thin out, the gaps between them become arbitrarily wide, and there is absolutely no deterministic formula that can point to the exact location of the next prime.
Which was the accepted truth until literally just days ago.
Yeah, on July 5, 2026, a massive, formalized paradigm shift closed its final theorems. It's called the Prime Gap Structure Research Program, or PGS for short.
And the sources we have on this are just staggering.
They really are. We're looking at the mathematical proofs, the GitHub READMEs, the raw structural data, and it all proves that the space between primes is not chaotic at all.
Not even a little bit. It is a highly ordered, readable, and entirely predictable architecture.
Which is just, I mean, the historical weight of this, it really cannot be overstated.
No, it can't. We're moving from a probabilistic model of prime distribution to a strictly deterministic one.
Meaning no more guessing.
Zero guessing. We are looking at a formalized framework that completely discards the whole idea of random primes and replaces it with this rigid, beautiful, arithmetic geometry.
So to really understand the magnitude of this shift, I feel like we have to first look at the flaw in the traditional methodology.
Right, the way we used to do things.
Yeah. The classical approach to finding primes, whether we are talking about, basic trial division you learn in grade school or massive computational algorithms, it is fundamentally a process of isolation.
I actually look at the classical approach as sort of a courtroom drama staged by accountants.
A courtroom drama. Okay, I like that. Break that down for me.
Think about how we currently identify a prime number. An integer is basically dragged into the light, completely isolated from its surroundings. We put it on trial.
Like a defendant on the stand?
Exactly. If it's a small number, maybe we just use trial division. If it's a massive cryptographic integer, we subject it to a Miller-Rabin primality test, or maybe the AKS algorithm.
Right, these really heavy, computationally expensive tests.
Exactly. We ask it very specific, pointed questions based on modular arithmetic, and at the end of this grueling procedure, the integer receives a binary verdict.
Prime or composite?
Prime or composite. Propose, test, reject. Over and over again.
So we basically treat the number line like a dark hallway, right? And we were just knocking on doors one by one, asking, hey, are you a prime?
Yeah, and if the answer is no, we literally throw the number in the trash and move to the next door.
And that procedure, it's just completely blind to the actual landscape.
Oh, totally blind. It's like trying to understand the topography of a mountain range by teleporting to random GPS coordinates, checking your exact altitude, and then immediately teleporting away again.
You'd never see the mountains or the valleys.
Never. The courtroom approach treats all the composite numbers, the non-primes that actually live in the gaps, as failed candidates.
Like they're just mathematical debris.
Exactly. Meaningless background noise that you just have to slog through until you finally bump into the next prime.
But the PGS framework, it flips that entirely, doesn't it?
Completely on its head, yeah. The composites aren't debris at all. They are the actual architecture of the number line.
Right, so we kept asking each integer in isolation if it was special, while the interval itself, the actual gap, was quietly laying out this exact readable map the entire time.
The illusion of empty space is the trap here. We see a prime, then we see a gap of composite numbers, then we see another prime. And historically, we just counted the distance and moved on.
Let's actually pull a specific prime gap from the sources to visualize this, because I think this is where it really clicks. So let's look at the space between the prime number 23 and the next prime, which is 29.
Okay, a classic small gap.
Right. Historically, number theory looks at that interval and just logs a raw distance of 6, a gap of 6. It's just treated as an empty void.
But if we stop looking at the distance and we actually start reading the internal structure of that gap, the void completely disappears.
So we look at the integers residing inside that space, 24, 25, 26, 27, and 28.
Right, and the PGS framework mandates that we analyze their divisor counts. We aren't testing for primality anymore. We are measuring the density of their factorization.
Okay, so let's walk through that. We take the integer 24, we map its divisors, which are 1, 2, 3, 4, 6, 8, 12, and 24.
So that gives 24 a divisor count of 8. It has a really high density of multiplicative structure.
Right, lots of factors.
Yeah.
Then we move to 25. Its divisors are just 1, 5, and 25. So that's a divisor count of 3.
Then we move to 26. Divisors are 1, 2, 13, and 26. That gives us a count of 4.
Okay, got it. For 27, the divisors are 1, 3, 9, and 27. So also a count of 4.
And finally, we hit 28, which has 1, 2, 4, 7, 14, and 28, giving it a divisor count of 6.
Okay, so our sequence of divisor counts for the whole gap between 23 and 29 is 8, 3, 4, 4, 6.
Exactly. And the moment you plot those integers on a graph, the gap stops being this empty distance. It suddenly has a distinct, readable internal shape.
Kind of like a valley.
Very much like a valley. And the absolute lowest divisor count inside that gap is 3, which is sitting exactly at the number 25.
This is the foundational observation of the whole framework, right?
It really is. Inside any prime gap, no matter how astronomically large it gets, if you list the divisor counts of the composite numbers, there is always a minimum value.
Right, it's not just random noise.
No, this structured list is a deterministic scalar field.
Now, I have to play devil's advocate for a second here, because anyone with a background in basic number theory might look at this and immediately point out a sort of definitional issue.
Ah, I know exactly where you are going with this, the tautology argument.
Yes, because a prime number is literally defined as an integer with exactly 2 divisors.
Yeah.
One in itself.
Right. That's the textbook definition.
So if we're just traversing the number line and tracking divisor counts, stating that the next prime is the first number we hit with exactly 2 divisors, it feels like a tautology, right?
It does sound like one at first glance.
It sounds like we're just restating the definition of primality, not actually predicting anything.
And honestly, that is the initial friction point for almost most mathematicians when they analyze this for the first time. They see that and say, well, obviously.
So how does the PGS framework counter that?
Because the endpoint hitting a divisor count of 2 is indeed just the definition of a prime. The actual revolution of the prime gap structure lies entirely in what happens before the endpoint.
Ah, okay. So it's not about the destination. It's about the mechanics of the approach.
Precisely. The sequence of composite numbers inside the gap, that 8, 3, 4, 4, 6 we just looked at, that is a deterministic sequence of arithmetic memory.
Memory. I like that word for it.
Yeah, those composites aren't just random failures on some primality test. Their divisor counts form a rigidly ordered field that actually dictates the precise moment the divisor count will inevitably drop back down to 2.
So the composites are actively pointing to the prime. They're signaling its arrival.
Exactly. And this is a big, but counting divisors locally between 23 and 29 is one thing. That's easy.
Right, small numbers.
If you want to prove this universally, you run into a massive scaling problem. A divisor count of 8 for a tiny number like 24 means something completely different than a divisor count of 8 for a cryptographic integer with 1,000 digits.
Oh, sure, because 8 divisors on a massive number means it's actually incredibly sparse in terms of factors, whereas on 24 it's super dense.
Exactly. You can't just use raw counts to map the entire infinite number line. It warps the perspective.
So you need a universal metric, something that normalizes the weight of these factors, regardless of how big the number is.
This was the major theoretical hurdle the research program had to clear, and they did it. They needed a shared scale that definitively separates primes and composites across any magnitude.
And the framework introduces this as the Divisor Normalization identity, or the DNI.
The DNI, yes. It's
Yeah.
an elegant piece of math.
Let's break down the mechanics of this DNI. The sources describe building this formula by calculating what they call the load a number carries.
Right, the structural load.
So to do this, they combine the divisor count, which is the raw amount of factor structure, with the integer's logarithmic scale.
The reliance on the natural logarithm here is absolutely crucial, by the way, because we are dealing with multiplicative building blocks.
Right, primes multiply together to make composites.
Exactly. And the natural logarithm is basically the native language of factorization.
Because multiplication in the arithmetic domain translates to addition in the logarithmic domain, right?
You nailed it. If we are trying to measure how much multiplicative structure a number possesses relative to its sheer size on the number line, the logarithmic scale is really the only clean way to measure that relationship.
Okay, so we have the divisor count and we have the logarithmic size. But just jamming them together leaves you with this messy, oscillating mathematical output, right? It's too noisy.
Very noisy. To create a truly universal baseline, the research applies a specific normalization scaling parameter.
Which the sources actually call a beautiful cancellation, which I love. Mathematicians get so poetic sometimes.
It really is beautiful, though. The scaling parameter they discovered is 5 equals a squared over 2.
$5 e 202.
Okay. When you run the combined load of the integer through an exponential Post transformation using this exact parameter, the complex, messy terms perfectly cancel each other out.
The noise just vanishes.
It vanishes completely, and you are left with this incredibly elegant equation. Zn equals knowledge to the power of 1 minus half its divisor count.
Wow. Let me repeat that so you can visualize it. For an integer $, its position on this universal scale is determined by taking $, and raising it to the power of 1 minus dn2.
Right. Let's apply the mechanics of this equation so we can see what it actually does.
Okay, let's test a prime number first.
Sure. If n is a prime number, what is its divisor count? dngn.
It's exactly 2.
Always 2.
Okay, so the exponent in our formula becomes 1 minus 2 over 2,
Which is 1 minus 1.
which evaluates to 0.
Oh, and any integer raised to the power of 0 is 1.
Boom, exactly. So every single prime number, whether it is 2, 29, or some multi-million digit Mersenne prime, maps exactly to ZO it as Egler over 1. That is wild. It isn't just an asymptotic approximation like we usually see in number theory.
No, it is an exact invariant baseline.
Okay, but what if 1 is a composite number?
Well, if 1 is composite, it inherently has a divisor count greater than 2.
Right, at least 3 or more.
That means dollars over 2 is strictly greater than 1, which forces that entire exponent to become negative.
Ah. And when you raise an integer to a negative exponent, the value drops strictly below 1. It becomes a fraction.
Exactly. The larger the divisor count, the more negative the exponent gets, and the closer the result gets to 0.
It creates a literal topographical map of the entire number line.
It does. The perfect mapping.
Imagine you are mapping gravity on an infinitely expansive, highly irregular planet. The DNI formula acts as this universal paving machine.
I like that. A paving machine.
Yeah, it creates a perfectly flat baseline, a zero excess ground floor right at 0 agulators in a Lamed bowl. And every single prime number sits perfectly flush on this ground floor.
But the composites.
The composites literally sink into the mathematical earth based on the weight of their extra divisors. A number with 3 divisors creates a shallow depression. But a highly composite number with 100 divisors, that creates a deep chasm.
And just like that, the DNI establishes a fixed prime-centered geometry. We no longer have to view primes as isolated spikes of anomaly in a sea of composites.
Right, the primes are the floor.
Exactly. Instead, primes form the invariant, flat foundation, and the composites are measured strictly by how far they deviate from that foundation. The universal geometry of prime gaps is now fully observable.
Okay, having a universal metric is beautiful. It is geometrically stunning. But it still begs the operational question, right?
How do we actually use it?
Yes. How do we use this flattened landscape to actually predict the arrival of the next prime?
And this is where the framework transitions from just being descriptive to being highly predictive. It introduces the concept of carriers and the gap winner rule.
Gap winner rule, or GWR. Let's dig into that.
The GWR is basically the engine of the entire methodology. We know that inside any gap, if you look at the divisor counts of the composites, there is a minimum value.
We saw that with the 23 to 29 gap, the minimum was 3.
Right. But in larger gaps, that minimum value often repeats. You might have several integers in the same gap that all share the exact same lowest divisor count.
Oh, interesting. So it's a tie.
Yes. The rule dictates that the selected composite, which is the true signpost pointing to the next prime, is always the first interior number from left to right that carries that lowest divisor count.
The leftmost minimum divisor carrier.
Exactly. Let's look at the gap between the prime 89 and the prime 97 as an example.
Okay, let me look at the data here. The composite numbers in that interval are 90, 91, 92, 93, 94, 95, and 96.
And tracking their divisor counts, we get 12, 4, 6, 4, 4, 4, and 12.
So the lowest divisor count in the entire gap is 4, but it appears 4 separate times. It's at 91, 93, 94, and 95.
Now, under a classical probabilistic model, this just looks like random noise. A four-way tie, nothing special about any of it.
But the gap winner rule resolves the tie geometrically, doesn't it?
It does. We scan left to right. The very first instance of that minimum count of 4 occurs at the integer 91.
Therefore, 91 is the GWR winner.
Yes. It becomes the selected composite for that gap.
And why is the selection of that specific leftmost integer so critical?
Because it activates what the sources call the no later simpler composite theorem.
That is a mouthful.
It is, but it's incredibly powerful. This theorem mathematically proves that once the GWR winner appears, so once 91 establishes the minimum threshold with 4 divisors, the next prime is mathematically guaranteed to arrive before any simpler composite can appear.
Wait, meaning you will absolutely never encounter an integer with 3 divisors after 91 before you hit the prime 97?
Never. The gap's structural descent is permanently locked at that point.
Wow. So the moment you identify the GWR winner, you know the descent into the valley is over. You've hit the bottom.
You've hit the bottom of the valley. The remaining integers in the gap are mathematically constrained. They are forced to maintain or exceed that divisor count until the structure inevitably breaks and ascends back to the prime baseline at 2.
Think of the GWR winner as the absolute lowest altitude waypoint in a valley between 2 prime mountain peaks.
That's exactly how it functions.
Once you cross that specific leftmost waypoint, you have deterministic proof that you can no longer descend. Every subsequent step is a forced trajectory toward the next peak.
And the framework actually goes even deeper into predictive mechanics with what they call the GWR supersignal.
The supersignal. They also refer to it as twin crime resonance in the papers.
Yes. This allows us to pinpoint the exact immediate closure of a gap.
This is where the structural evidence just becomes undeniable. They found a trigger that guarantees the prime is the very next integer. Like, no more walking up the valley, the prime is right there.
Exactly. You take the GWR winner, that leftmost minimum, and you cross-reference it with its modular primordial resonance.
Okay, unpack that. Modular primordial resonance.
It sounds complex, but we are basically just looking at the remainders when the winner is divided by specific primordial bases. 2, 3, 5, 7, 30, 210, 23, 10, and so on.
These are just the products of consecutive primes, right? Like 2 times 3 is 6 times 5 is 30.
Exactly. We check how many remainder zeros it triggers across those specific bases.
Remainder 0 just means it divides perfectly without a remainder.
Right. And the data analyzed in the sources, spanning over 1 million prime gaps, proves that if the GWR winner triggers 4 or more remainder zeros, the gap closes immediately.
The very next number is a prime. Let's trace the logic of why that actually happens mechanically.
Sure, if a number has 4 or more remainder zeros against those primordial bases, it must be a multiple of 30.
Because the product of the first 3 primes, 2, 3, and 5, is 30. So if it hits 4 zeros, it's definitely hitting those first 3.
Right, and the minimum possible divisor count for any multiple of 30 is 8.
Okay, I follow.
Now apply the core definition of the GWR winner. It must possess the absolute minimum divisor count in the entire gap. How is it mathematically possible for a number with at least 8 divisors to be the minimum in a gap?
Oh, I see it. It can only hold the title of minimum if there are no other composites in the gap at all.
Exactly. Because if there were other composites, They would almost certainly have fewer than 8 divisors, right? Like a number with 4 divisors or 6.
Which would steal the GWR winner title away from the multiple of 30.
Precisely. For a multiple of 30 to successfully defend its position as the GWR winner, it must exist in total isolation.
It has to be the only composite number in the entire interval.
Which means the total gap size is exactly 2.
So the moment your algorithm detects a GWR winner, triggering that 4-0 supersignal, it is a deterministic arithmetic guarantee that the very next integer is a prime.
There is zero probability involved. The arithmetic structure of the composites acts as a direct readable signpost.
We are no longer guessing at the distribution of primes. We are literally reading the structural code of the composites that dictate their placement.
It's a fundamental change in how we interact with numbers.
But, and I know you know this is coming, this naturally leads to the most critical vulnerability in the entire theory, or at least what seems like a vulnerability at first.
The unbounded stretch problem.
Yes. We know how to find the signpost. We know how to read the floor of the valley with the GWR winner. But what physically prevents the valley from stretching endlessly?
Right, like what if the valley is just flat for a billion miles?
Exactly. You find the GWR witness, but what if the mathematical ascent back to the prime peak takes millions of digits? What prevents the distance between the signpost and the next prime from being arbitrarily vast?
This is the exact problem that has haunted number theory for centuries. And it is the precise problem resolved by the theorem closed on July 5, 2026.
The prime square proximity theorem.
Yes. This is the absolute climax of the PGS proofs. It provides the deterministic mechanism that strictly compresses prime gaps. It forces them to close.
The logic of the prime square proximity theorem is heavy, I won't lie. But reading through the sources, it is flawless.
It is incredibly tight logic. It specifically examines the scenario where the GWR witness, our lowest waypoint, happens to be the exact square of a prime number.
Okay, let's walk through this slowly. Let's denote our prime square as 3 squared.
A prime square inherently has exactly 3 divisors, right? One, the root $3, and the square itself $3 too.
Just 3 divisors.
Yeah.
Very sparse. Now, if the 2WR2 is the GWR witness for a gap, it means it is the leftmost integer in that gap to achieve that incredibly low divisor count of 3.
Yes. And because it is the leftmost minimum, it mathematically enforces a strict condition on every single integer that preceded it in the gap.
Because if any integer before 2W had 3 or fewer divisors, that earlier integer would have been the GWR witness instead.
Exactly. Therefore, every single integer residing in the gap prior to the prime square must be composite because we are inside a gap and must carry a divisor count of 4 or more.
So they have to be highly factorable.
Right. To maintain a divisor count of 4 or more, these integers must be constructed from prime factors that are strictly smaller than the root $3.
The sources describe this as root-straddling factorization.
It's a great term for it. You have this continuous sequence of integers leading up to the prime square, and they all have to be perfectly tiled by a specific, limited set of smaller prime factors.
Imagine trying to perfectly tile an incredibly long hallway, but you are only allowed to use a handful of small, specific tile shapes.
And you cannot leave any empty space, because an empty space represents a prime number, and we are assuming this entire sequence is entirely composite.
Right, we're trying to stretch the gap. But the math reveals a fatal contradiction in this tiling process, doesn't it?
A massively fatal contradiction. There is a geometric limit. The sources detail a continuous square root width band immediately below the root $4, where these smaller prime factors are explicitly and mathematically forbidden from existing.
Forbidden from existing, so the required tiles are just missing.
They don't exist. The density of available prime factors smaller than $2 is strictly insufficient to perfectly tile those rapidly expanding composite rows.
So what is the mathematical consequence of having insufficient prime factors to maintain the composite sequence? What happens to the tiles?
The factor structures are forced to overlap. Because they cannot cover new geometric ground, they intersect and crash into each other.
A collision.
The research defines this as the modulus link collision. This unavoidable arithmetic collision proves that the integer space absolutely cannot remain entirely composite up to an arbitrarily large length.
The factor collision literally forces the sequence to break, which forces a prime to emerge out of the wreckage.
Yes. The distance from the signpost to the prime is deterministically bounded by the available factor geometry. It cannot stretch endlessly.
The gap is mathematically compelled to close.
Compelled to close. It's a structural inevitability.
Which fundamentally replaces Cramer's classical conjecture.
Oh, entirely. Anyone familiar with analytic number theory knows that Harold Kramer established hypothesized bounds on prime gaps decades ago.
But Kramer's model was entirely probabilistic.
Right. He modeled primes as independent coin flips. He used a Poisson distribution to guess the maximum distance between a prime dollar and the next prime dollar.
It was a statistical guess based on historical averages. But the prime gap structure provides the actual underlying physical mechanism.
It doesn't rely on the probability of coin flips. It bounds the offset distance from the left prime to the GWR selected witness using exact, rigid arithmetic.
It proves that exceeding Kramer's scaled limits wouldn't just be statistically unlikely, right?
Yeah.
It would force an impossible mathematical contradiction, that modulus link collision.
It's the difference between predicting weather patterns based on reading a farmer's almanac and predicting rain by physically tracking the collision of atmospheric molecules.
We have completely moved from statistical modeling to deterministic mechanics.
And by establishing this deterministic arithmetic foundation, the prime gap structure effectively dethrones the most famous, heavily relied upon conjecture in the history of mathematics.
You are talking about the Riemann hypothesis.
I am.
The sources dedicate a massive section to this. They explicitly state that the Riemann hypothesis is now an obsolete dependency for these exact prime structure methods.
To understand why that is such a seismic shift, an earthquake in the math community, we have to look at the conditional regime that currently dominates analytic number theory.
Right. Explain how that works for us.
For over a century, mathematicians have relied on the complex geometry of the Riemann zeta function to estimate the distribution of primes.
Because we didn't have the internal arithmetic mechanics like the divisor counts, we were blind to it.
Exactly. So we had to look for a continuous overarching function that could approximate the chaotic behavior of the primes. The Riemann hypothesis posits that all non-trivial zeros of the zeta function lie on a specific critical line in the complex plane.
The famous critical line.
Yes, and if this is true, which we heavily assume it is, it provides incredibly tight bounds on the error term in the prime number theorem. It controls the wild oscillations.
So whenever a mathematician needs to prove a theorem about prime distribution today, but they can't resolve the chaotic error terms, what do?
They simply assume the Riemann hypothesis is true. They build conditional proofs. They state, assuming the foundation of the Riemann hypothesis holds, this theorem about prime gaps is true.
It basically became an architectural crutch for the entire field.
It really did. But the PGS framework argues that we no longer need to assume the complex, continuous geometry of the zeta function zeros to understand the discrete behavior of primes.
Because the conditional analytic estimates can be entirely replaced by the exact deterministic arithmetic of the divisor count structure we just talked about.
Exactly. But, and this is a crucial step the researchers had to take, you can't just discard the Riemann hypothesis without proving that your new arithmetic framework perfectly accounts for the phenomena the zeta function describes.
Right. You can't just say, we don't need it, without proving why your new tool does the exact same job.
So the research establishes what they call an analytic bridge.
I found this part of the proof fascinating.
It really is. They prove that the local arithmetic of the prime gap structure, those raw divisor counts, maps flawlessly to the classical continuous geometry of Riemann.
How exactly is the bridge constructed?
It's constructed using Dirichlet series. The framework takes the native discrete objects of PGS, the raw divisor counts and their logarithmic loads, and encodes them into a generating function.
Right. We take that specific D&I logarithmic load, the one incorporating that $y equals e to unctum 2 scaling parameter, and we build a series.
And when you combine the Dirichlet series of the divisor counts with this specific generating function, the mechanics of the D&I scaling parameter force a massive algebraic cancellation.
Just like we saw with the individual numbers, but on a macro scale, all the messy, localized integer noise completely vanishes.
Yes. And what emerges from the cancellation evaluates mathematically to exactly negative zeta prime of zero zeta of 0.
Wait, which is the classical logarithmic derivative of the Riemann zeta function.
It is the exact mathematical object that generates the von Mengelt function, which is the universal prime power detector at the heart of all zeta function analysis.
Wow. So by simply tracking the integer-level divisor counts and applying the correct geometric normalization, the framework natively reconstructs the exact prime detector that the Riemann hypothesis was built to protect.
We recover the function natively, without ever needing to assume the hypothesis.
So the Riemann hypothesis is exposed not as the foundational rule of primes, but as a downstream analytic description.
It is merely a continuous compressed shadow of the exact, discrete structural rules governed by the PGS at the integer source.
I was trying to think of an analogy for this while reading the papers. Imagine you are an architect trying to deduce the exact floor plan of an incredibly complex building, but you aren't allowed inside.
Okay, I like where this is going.
The Riemann hypothesis is the equivalent of standing on the lawn, watching the shadow the building casts as the sun moves, and using complex continuous mathematics to guess the layout of the interior rooms based on the oscillations of the shadow.
Right. It is a brilliant, beautiful piece of deductive reasoning, but it is fundamentally indirect.
Exactly. The prime gap structure, on the other hand, simply unlocks the front door, walks into the building, and reads the original blueprints.
We don't need to analyze the geometry of the shadow if we hold the exact arithmetic mechanism that physically constructs the walls. The conditional assumptions of the shadow are obsolete because we possess the deterministic reality of the structure.
Okay, we've spent a lot of time dissecting the philosophical shift, the deep arithmetic mechanics, the deterministic bounds, and the dethroning of the Riemann hypothesis. But I want to pivot, because we have to look at what this structural blueprint means for the real world.
Oh, the engineering implications are massive.
This isn't just a victory for theoretical chalkboards. The sources detail a massive, immediate application in the field of cryptography.
Modern digital infrastructure, secure communications, banking, data encryption, it is overwhelmingly reliant on RSA encryption and Diffie-Hellman key exchanges.
And those protocols rely entirely on the rapid generation of massive, cryptographically secure prime numbers.
Exactly. And how do our current cryptographic systems generate those massive primes? They use the courtroom drama we talked about earlier.
They rely entirely on proposed test reject.
Right. Current generators utilize random number algorithms to basically spit out massive composite candidates and then subject them to computationally expensive primality tests like Miller-Rabin.
And if the integer fails, which it usually does, it is discarded, and the system randomly guesses again.
It is a massive expenditure of computational power to blindly test numbers that we now know are actually part of a readable structural grid.
So enter the prime gap structure framework. It introduces a totally new paradigm for prime generation.
A PGS generator doesn't guess. It reads the divisor count structure of the integer sequence and navigates directly to the endpoint.
But the implementation of this wasn't exactly smooth, was it? The sources outlined this incredible engineering drama when the team was trying to scale this up.
Ah, yes. The deep band endpoint transport probe. This is where theory met harsh computational reality.
Walk us through what happened with the deep band probe, because this sounds like something out of a sci-fi movie.
Well, the team was traversing these massive prime chains, right? And they were using the PGS framework to leap from gap to gap. Everything was running perfectly at the lower bit scales, but then they hit a computational wall at the 103-bit scale.
The 103-bit scale, what exactly happened?
The divisor count fields at that magnitude became so incredibly dense that the memory allocation on their systems basically gridlocked. The structural descent finding that GWR winner, it triggered an 11-hour system hang.
An 11-hour hang. The whole system just froze.
Froze solid.
Yes.
The algorithm was trying to hold the entire topographical map of the 103-bit gap in memory all at once to find the leftmost minimum, and it just choked.
Wow. So how did they bypass that? Because obviously they did, given the results we're seeing now.
It was a stroke of engineering genius, honestly. They realized they didn't need to hold the entire valley in memory at once. They engineered a mathematically exact, array-segmented sieve.
An array-segmented sieve.
Yes. Instead of mapping the whole gap, the segmented sieve reads the divisor structure in small localized chunks, identifies the minimum strictly within those bounds, and then mathematically proves whether that local minimum is the absolute global GWR winner without needing to see the rest of the map.
That is brilliant. It's like, instead of trying to look at the entire mountain range from orbit, they just built a localized radar that sweeps forward, confirming the lowest point as it goes.
Exactly. It bypassed the memory bottleneck entirely. And once they implemented that segmented sieve, the performance metrics just exploded.
The immediate practical breakthrough here is the pre-filter efficiency for RSA key generation. By utilizing the exact DNI formula as a structural pre-filter, the algorithm analyzes the load of the candidates before they ever reach a primality test.
Right. It looks at the structure first.
And the deterministic data measured in the sources shows that the PGS prefilter rejects approximately 91% of composite candidates instantly.
In 91%, they never even trigger the expensive Miller-Rabin test. They are just mathematically recognized as composites and bypassed.
And the measured speedups are undeniable. By navigating the modulus link structure natively, the framework achieved a measured 2.09x speedup for generating 2048-bit RSA keys.
More than twice as fast, and the beautiful thing is, as the integers get larger, the structural efficiency actually scales.
Right, at 4096 bits, the speedup increases to 2.82x.
We are talking about nearly tripling the computational efficiency of generating the cryptographic keys that secure the modern internet.
And it's all simply by acknowledging that the space between primes is not empty.
The project has actually evolved now to feature a general deterministic PGS native RSA endpoint engine. It traverses locked endpoint chains using only the structural rules of the gap. It completely bypasses the need for random probabilistic guessing.
Which means we have fundamentally changed how we view the integers. We've stopped treating them as isolated points in a chaotic void, and we are finally recognizing them as an interconnected, deeply structured ecosystem.
It is a profound transition from observing chaos to reading underlying architecture. The prime numbers haven't changed. Our capability to perceive their geometry has.
For millennia, primes were the ultimate symbol of mathematical unpredictability. They were the definition of noise scattered across the number line.
But by simply shifting our perspective,
Yeah, by turning our attention to the divisor counts of the composite numbers living in the gaps, we revealed an incredibly rigid, beautiful, and deterministic reality.
the divisor normalization identity provided the universal scale.
The gap winner rule revealed the internal signposts,
The modulus link collision proved the intervals cannot stretch endlessly.
and the analytic bridge proved that this simple, discrete arithmetic perfectly reconstructs the massive, complex, continuous geometry of the Riemann zeta function, rendering its conditional assumptions totally unnecessary.
This breakthrough is a powerful reminder that when a system appears chaotic, it is almost always just a failure of our measurement tools.
Questioning our most entrenched assumptions, like the assumption that the space between primes is devoid of structure, is the mechanism of revolutionary discovery.
It makes you wonder what else we are looking at blindly.
It really does. If prime numbers, the absolute mathematical gold standard for randomness and chaos for the last 2,000 years, are actually governed by a hidden deterministic structural code just waiting to be mapped, what other seemingly chaotic systems in our universe are waiting for their underlying architecture to be read?
Right.
Are we looking at the chaotic fluctuations of quantum mechanics, the unpredictability of genetic mutations, or the turbulence of fluid dynamics, and assuming they're fundamentally random simply because we haven't yet discovered their version of a divisor count?
It is the ultimate scientific question, isn't it? What else in our universe is just a shadow on the lawn waiting for us to unlock the door and read the original blueprints?
We began by talking about the comfort of a diagnostic X-ray. For centuries, mathematics has been staring into the murky, unpredictable waters of the prime numbers, trying to guess what structural mechanics lay beneath. Today, thanks to the prime gap structure, the waters are no longer murky.
We finally possess the X-ray.
We possess the X-ray, and the underlying architecture is flawless. Keep exploring, keep questioning the chaos, and we'll see you in the next deep dive.